Hi. Hi, welcome to this lab video. I'm today in the BM lab at the Karl Landsteiner University in Krems, and I'm conducting a small project myself which is about measuring the viscoelastic properties of meniscus tissue. The meniscus is the soft tissue part in your knee. This is a meniscus of a pig, which already has 2 samples punched out of it. And the goal of this project is to determine storage and loss modulus and damping, so the classical viscoelastic properties. Why is this interesting? It is interesting because we test the tissue at different conditions, let's say. So the baseline condition is the fresh tissue directly received from the animal, but then the tissue is stored in different solutions. So the first solution is 0.9% saline solution, which is the body buffer solution, but then to make it more resistant to decay, it is also stored, so other samples are stored at 26% of saline solution, and also another batch of samples is sterilized with a certain process that is conducted at a company we are collaborating with. So we have meniscus tissue at different preparation or processing stages, and the question is how the viscoelastic properties are changing. Is the tissue degrading? How is damping and stiffness changing depending on the storage medium or the processing stages? For doing this, I take a meniscus like this and I punch out cylindrical samples. Maybe you can see this here. There are 2 samples already punched out. They have a diameter of 6 millimeters, and they are tested in our small testing machine in saline solution. So I will show you how this works. Let's go. I will now extract a 3rd cylinder out of this meniscus, but first I will measure the shore hardness, which is also another type of material property. I have here a shore durometer, which is working like this. You have a small indenter here at the end, a small tip, and you press this tip on the surface and wait for a few seconds, and then the device is giving you the shore hardness, which is basically related to the indentation depth of this pin. So the deeper it indents, the higher the lower the shore hardness. So let's turn it on. It reads 0, and then can you see that? Pressing it here against, wait a few seconds. Okay, and you have a value of 68, and I do this 5 times and the device is automatically averaging those values. And it is always around 60 or 55 to 70. I have now measurement 5 of 5, and the average measurement is 64.7 shore hardness. 64.7. So what I always do is I try to keep as much information visible and clear all the time. So this is sample number SM6_1. We have cylinder position ABC, and I'm now extracting cylinder number C with this tissue punch of 6 millimeter diameter. Okay. I'm planning to do compression tests, but this is not possible with this shape. As you see, the bottom and top surface is inclined, so it's not a perfect cylinder. What I made for cutting is this cutting guide. It has slots here at a certain distance, so this is 6 millimeters. I will cut now sample. I have a perfect cylinder. So let's take the sample to the machine. So I'm putting a sample in the test setup. And try to center it. Okay, what is the test setup doing? The test setup consists of two pieces. One is this bath here. It's filled with saline solution. It has a flat bottom, and the sample is put just on the bottom of this container. And at the top you see a rod, which has a nice perpendicular surface to that surface, and with this rod I'm compressing the sample during the test. So this is a so-called unconfined compression test. That means the sample can expand in circumferential direction as the sample would like. At the top and at the bottom surface the conditions are unfortunately undefined. We have some friction there and also some sliding, but this is how it is when you do mechanical testing of biological tissues. You cannot control everything perfectly. You have to do what is possible. This is the software, and now what test protocol are we applying? It is a relaxation test we are doing. That means we are applying a step load, tuck, on the sample and wait and measure how the force signal is evolving over time. So the question is, at which strain level are we doing this test? And what I found in other publications, and which seems to be also physiologically relevant, is a strain of 12%, and this corresponds to 0.72 millimeters of step displacement. This is our specimen SM6_1_C. The next step is to apply preload. This is the force signal. I'm zeroing it, and to ensure good contact between the top and bottom surfaces, I'm applying around 0.1 Newton of preload. Here. Okay, that's good. Okay, ready. Let's start the test. Okay, the test is running. You see the force over time plot here. The step load was applied here, and the force signal reached to 55 newtons, but then was dropping rapidly and is now relaxing over time. The test is already running 60 seconds. We will run it for 300 seconds. And you see that the meniscus tissue is clearly viscoelastic, because for the same displacement, the displacement is always the same. It was applied at second 0 or 1, and then it stayed the same, but the force is dropping over time. The tissue is relaxing. Okay, the test finished. Let's get the sample out of there. So that was the test. A nice relaxation plot. And what you can do now is extract storage and loss modulus out of this relaxation curve by using the Prony series. Okay, let's find out how to evaluate the test data to extract our material parameters. The test data itself, which we recorded with the machine, looks like this. It is a text file containing data over time. We have the time points here in this column. We have the displacement in the middle and the force signal here. And these signals run from 0 to 300 seconds. To go from the structural space, so from force and displacement dimensions, to the material space, so stress and strain, we need to convert our force and displacement data to stress and strain data. We do this here as easy as we can do it. So we apply the engineering stress and engineering strain method, which is valid for small displacements. How is this working? Our meniscus looks like this, a cylindrical shape, and the stress is simply calculated by dividing the force signal by the cross-section area, A0. Also quite easy, the strain is calculated by dividing the displacement by the initial height of the meniscus. And this gives us two plots like this. So now it's strain over time and stress over time, and we see that we applied 12% of strain, exactly what I wanted to achieve. It is quite high to use engineering notation, so engineering stress and engineering strain, but for the sake of simplicity we are doing this right now in this way. So we have our relaxation curves in stress and strain space. The next thing to do is to use a model and to fit it to this test data. We use for this purpose a generalized Maxwell model with 3 layers. So unlike it's plotted here with n layers, we use one with 3 layers. The model itself consists basically of an arrangement of springs and dampers. When you do this optimization process, you get a fit like this. In red, the model response can be seen, and below that in blue you see the experimental values, and the overlap, so the fit, the goodness of fit is very good. So the selection of this model was obviously a good choice. As a result of the optimization process, we get 7 material parameters, so 4 ease and 3 relaxation times. These are not easy to interpret. Just to give you an example, the E infinity is the quasi-static or long-term modulus. This is the stiffness you feel when you push or pull very, very slowly on the meniscus. And as it turns out, this 16 megapascal is a quite good value and corresponds to literature reports quite well. Okay, after some mathematical operations, you can transform those 7 values into 3 values, into more well-known material parameters. They're called the loss factor, tangent delta, the storage modulus, and the loss modulus. For doing this transformation, you have to select a frequency, and I was selecting 1 Hertz as it corresponds quite well to the gait frequency of a human being, and we're talking about meniscus, so this is a logical consequence, I guess. So this is the end result. We have now storage, loss and loss modulus and tangent delta of our sample SM6 1C, and that's it. All tests are finished. I'm cleaning up now. Have a good day. Bye bye. Meniscus from a sheep. Nein, das stimmt ja gar nicht. Das ist ein Schwein.